Now let's talk about work. So far we've been talking about conservation of energy, right? But what we want to do now is talk about how can you change the energy of a system. How can you change the energy? We've been talking about conserving energy, right? In all the situations in which energy is conserved, what do we do? What kind of equations do we set up and so on? Now is the time to talk about how do you change the energy of a system, okay? So consider two people throwing a ball, right? So the first person that is going to throw that ball is going to have to start with the ball at 0 kinetic energy and leave it with some kinetic energy that is not 0. So that person is going to have to increase the kinetic energy, right? So when you throw that ball, that's what you're going to do. The ball is going to be caught by the other person who has to do what? The ball is coming with some kinetic energy. When you catch it, you want to slow down that ball and bring it to 0. Okay? So the second person is going to have to decrease the kinetic energy, decrease the energy of that ball. The first person increases the energy of the ball. The second person decreases the energy of the ball, right? Delta K in the first case will be bigger than 0. Delta K in the second case is negative. So the question is, how do I manage to do that? How do I manage to apply force to a ball in which in one case that force is going to increase the kinetic energy. In the second case, that force is going to decrease the kinetic energy. Okay, what do I have to do to make sure that that's what happens there? So in the first case, I'm applying a force, and the ball is moving in the direction of the applied force. Right? My initial position and my final position determine that my displacement vector, say, it's to the right. And the force that I have to apply to accelerate that ball is in the same direction. Right? So that's in the first situation. In the second case, what's happening is that the ball is coming at you with some velocity, and you want to slow it down, so you want to put an acceleration that is in the opposite direction. Your force is going to have to be to the left to make sure that that velocity, initial velocity, goes down to 0. So in the second case, your force and your displacement vector are opposite in direction. Okay? In the first case, force and displacement are in the same direction. In the second case, they're opposite. Okay? So that accounts for the difference in the outcome. In the first case, when the force is in the same direction, that force will increase the energy of the system. In the second case, when the force is opposite to the displacement, that force decreases the energy of the system. Okay? So you can use a force to increase the energy of a system, or you can use a force to decrease the energy of the system. It depends on how you apply that force. So let's look at a specific case of a force applied to a block sliding on a frictionless surface, and that force is going to be applied at an angle theta. So what I want to do is I want to find out how does the kinetic energy of this object change, and to relate that change in kinetic energy to the force that I applied, the distance that the object traveled, right? I want to connect those two things, the force on one side and the change in kinetic energy on the other side. Okay, so that force was constant over the interval, the distance delta S. That's my displacement from the initial to the final. The kinematics equation for constant acceleration, there is one that tells me that the velocities squared are related to each other. So in this problem, we have some initial velocity. I didn't specify how much that was. It could be some VI that is not 0. So this kinematics equation tells me that V final squared minus V initial squared is 2 times the acceleration times the displacement. Okay? At this point, you should be pretty familiar with that one. We've used it a lot. So if I multiply by 1/2, remember that I'm trying to get to the difference in kinetic energy. So I'm going to use that kinematics equation and multiply by 1/2 of the mass of the block. So what it says is that I have constructed the difference in kinetic energy on the left-hand side. On the right-hand side, I have 1/2 of the mass times 2 times the acceleration times delta S. Right? This says 2 times the acceleration times delta S. I just multiply by 1/2 of the mass on both sides, nothing else. 2 can cancel. And what I have on this side is the mass times the acceleration times delta S. Mass times acceleration times delta S. So that equation says the difference in kinetic energy between the final and the initial situation is equal to ma times delta S. What's ma? ma is the net force acting on this system, right? The net force is a force that goes in the x direction, right? The only force in the x direction is F cosine theta. F is the only force with x component. So the net force in the x direction is F cosine theta. In the y direction, the net force should be 0 because that block, it's going to slide on that surface, right? I'm not pulling too hard to get the block to fly in the air. I'm just dragging it by pulling at a certain angle, okay? So in the y direction, I'm going to assume that there is no acceleration. The net force in the y is 0. That's what I just said. The net force in the x direction is F cosine of theta. So that is equal to ma. So in my equation at the bottom that says ma times delta s, I can replace, instead of ma, I can plug in F cosine theta. So when I do that, I will get final kinetic energy minus initial kinetic energy equals, instead of ma, I put F cosine theta, and we still have delta S multiplied. So this is my equation that now relates force, displacement, the angle showed up there. Maybe you were not expecting that. And that product of those three quantities should be equal to the change in the kinetic energy of the block. Okay? So that's how that force is going to change the kinetic energy. It will depend on for how long you apply the force. That's your delta S. Does that make sense? If you apply a force F, but only for half a second, you don't get the same change in kinetic energy than if you apply the force for 10 seconds, right? Because remember that as long as the force is applied, that object is accelerating. So it's gaining kinetic energy, okay? So obviously the delta S should show up there. How much force is applied obviously is a factor, but maybe the unexpected part was that the part of the force that is perpendicular to the displacement doesn't matter, because I only have the F cosine theta part there, okay? So that is only the parallel component of the force to delta S. That's what matters, right? Remember that we have said that when a force is perpendicular to the displacement, it doesn't change the energy of the system. This is where it's coming from. If F was perpendicular to the displacement, if F was along the normal, right, obviously there will be no change in kinetic energy, right? So like I said, the change in kinetic energy is given by the parallel component of the force. Parallel to what? Parallel to the displacement. That's what matters. Only that component. So if that's the vector F and the vector delta S with an angle theta between them, the F parallel is the component of F, F cosine theta, that goes in the direction of delta S. This F parallel delta S, or F cosine theta delta S, there is a definition in math about the dot product between two vectors. That definition says that if I have vector A and B, as you see in the picture, A pointing in one direction, B in another, if the angle between them is theta, then I define this operation A dot B. It's a sort of funny multiplication, right? With vectors, you can just multiply the vectors, right, one times the other because they have directions. So this is a kind of funny multiplication where you multiply the magnitudes, but you throw in the cosine of the angle between them. Okay? That's called the dot product. With that definition, if you have the vector, unitary vector in the x direction, I hat, and the unitary vector in the y direction, j hat, and you do the dot product between those two, what do you get? So that thing will be equal to the magnitude of I, which is 1. The magnitude of j is 1, so 1 times 1. But then there comes the cosine of the angle between them. The cosine of the angle, that's how I define the dot product between two vectors. It's not just the A times B part, but there is the cosine also. So what's the cosine of the angle between I and j?
1.
The angle is how many degrees? 90. So the cosine of 90 is 0, right? So that dot product is a 0. I is 1 times j 1 times the cosine of 90, that gives you 0. So if two vectors are perpendicular, you get the dot product being 0. if you do the dot product between I and I, you get 1, because now the angle is 0. So the cosine of 0 is 1. 1 times 1 times 1, 1. J with J, same deal. So if you use that, we can write the product, the dot product between A and B in terms of their components. Not in terms of A, magnitude of A times magnitude of B times the cosine, but also we can express it in terms of the components. So let's do that. A has component AX in the I direction plus AY in the J. B, same thing. So we do the dot product between those two. And what you do is you multiply the first term times the second one. Do the dot product between the first term and the first term on the other one. So that's AX, BX, I hat, dot I hat, which is 1. So that's just AX, BX. Then AX with BY. That's a 0 because you have the I hat and the J hat together. Dot product between those two is 0. Then you have this, AY with BX. That's another 0 because you have J hat and I hat together. And the last one is AY with BY. And that's J hat dot J hat, that's a 1. So your final answer for A dot B is AX BX plus AY BY. So there's two alternative expressions for the dot product between two vectors. If you have the magnitudes and the angle between them, you're good, use the bottom one. But if you have the vectors in components and you want the dot product, then multiply the x components and add the multiplication of the y components. Okay, depends on what information you have. So that's a little parenthesis here to remind you of dot products if you're not familiar with them. So we're going to use the dot product to write this expression, to rewrite this expression. We have delta k equals f cosine theta delta s. So how do I write that in terms of a dot product? So the dot product between vector f and delta s as vectors. If those two vectors made an angle of theta, then their dot product will be f cosine theta delta s. So I'm going to define that quantity. Since it showed up in the change in the kinetic energy, it seems like an important quantity. Whenever there's a force acting on a system and that force acts over a certain distance delta s, I can tell that the difference in kinetic energy is going to be equal to F dot delta S. So I'm going to define that and call it work. So the work done by force F, I'm going to define it as, if F is constant, I'm going to take the force F and do the dot product with delta S. Okay? That's how I'm going to define the work of the force F. Now notice that in this problem that we have here, the block moving under the force F, there's other forces. There's the normal force, there's the weight of the block. So those other forces, according to my definition of work, would do also work. I can calculate the work done by these other forces. So the work done by the normal will be the normal force dot product with delta S. How much is that? That should be 0 because the normal force and delta S are perpendicular to each other. So the normal force does not change the energy, right? We had said that before. The other force is gravity. The work done by gravity in this motion will be the vector gravity, which I'm going to write as minus mg vector, dot product with delta S. That's another 0 because g points vertical down, delta S is horizontal. 90-degree angle between them, or I guess minus 90. So that the dot product is 0 one more time. So in this problem that we're discussing, the only force that is doing work on that block is the force of, that's F, the force, the applied force in the red vector up there. That's the only force that is doing work. And the amount of work that it does, it's equal to the change in the kinetic energy of the block. Now in general, what you have is, what you should use is that the work of the net force is what's going to change the kinetic energy of the system. It's W net, not just the work of one of the forces. Okay? What happened in this problem is that the other forces gave us 0 work. Okay? So what you have to do is you add the work done by all of the forces acting on the system. If you have a force 1, F2, F3, and so on, the net work will be the work done by force number 1 plus the work done by force number 2, etc. You add that, and that's the quantity that you're going to say that it's equal to the change in the kinetic energy. Okay? In this example, as I said, if F1 was F, this was the normal and the other one was gravity, these two terms were 0. So our work, net work, was just the work done by F. And that turned out to be, of course, equal to delta K. So again, this is very important. The net work done on the system is what changes the kinetic energy, and that net work should be the sum of the work done by every force acting on the system.